In May 2025, astronomers using the Íinوي solar telescope captured the sharpest image of the sun ever taken, revealing ultra-thin magnetic stripes, just 20 to 50 kilometers wide, etched across its surface. These newly observed photospheric striations aren't tied to solar flares, but show a hidden magnetic layer shaping the sun in subtle ways. This breakthrough marks a new era in solar science, turning once theoretical structures into a visible reality. The discovery focuses on fine, bright and dark stripes along the edges of solar granules, convective cells on the sun's surface. These patterns weren't tied to any major solar event. They appeared during routine high-resolution imaging. Captured by the world's most powerful solar telescope, the 4-meter Daniel K. Íinوي solar telescope, the images came through its visible broadband imager tuned to the G-band, 430 nanometers, a wavelength especially sensitive to magnetic features. Each stripe was found to correspond with localized magnetic field variations of around 100 Gauss, equivalent in strength to a household magnet. These variations subtly affect the opacity and density of the surrounding plasma, shifting the depth at which light escapes, an effect known as the Wilson depression. This produces slight changes in brightness visible in high-resolution imagery. Before this, similar features had been theorized in simulations, but had never been observed directly. What's important is not just the appearance of the striations, but that they signal the presence of fine-scale magnetic fields interacting with the sun's convective surface in ways we couldn't resolve until now. The ability to detect them comes down to resolution. At 20 kilometers per pixel, this level of detail marks a breakthrough in how finely we can observe the photosphere from Earth. In previous telescopes, features smaller than 100 kilometers across were indistinguishable from background fluctuations. To confirm the finding wasn't an observational artifact, the team compared their images to state-of-the-art magnetohydrodynamic MHD simulations of the solar surface. These physics-based models had independently predicted similar striated structures. The match between simulated and observed imagery was striking, confirming that these were indeed real magnetic features, not processing noise or instrument error. The detection of photospheric striations has significant implications, not only for how we view the sun, but for how we model it, forecast its behavior, and even interpret other stars. For decades, solar magnetic research focused primarily on large-scale features, sunspots, solar flares, and coronal loops. But these new striations show that magnetism plays a role at much smaller, quieter scales. It suggests that the sun's magnetic architecture is far more intricate, potentially forming a multi-layered structure embedded throughout its outer layers. The key scientific value of this discovery lies in what it confirms. For years, high-resolution simulations predicted that fine-scale magnetic sheets could ripple along the edges of convection cells. Now, for the first time, we've directly observed those effects, lending new confidence to solar models used in research and forecasting. These validated models can now be refined further. They help us understand not just surface brightness changes, but also energy transport, magnetic reconnection, and wave generation, all of which are involved in the heating of the solar atmosphere and the origin of space weather events. This matters for Earth because most disruptive solar activity, like flares and coronal mass ejections, begins with magnetic instability. Understanding how magnetism operates at small scales improves our ability to forecast when and where these events may occur. There's a cosmic angle, too. Similar magnetic striations appear in star-forming regions, suggesting this pattern spans across scales. By studying them on the sun, where we can see them clearly, we gain a blueprint for understanding distant systems. They also help explain subtle fluctuations in solar brightness, refining models of past and future solar activity. The discovery of striations is just one of the first scientific milestones for the Daniel K. Inouye Solar Telescope, which officially began science operations in late 2022. The telescope was specifically designed to study the sun's magnetic fields from the surface up into the corona, where solar winds originate. Now that researchers can identify and monitor these ultra-fine features, the next step is to observe how they evolve. Do they stay stable for hours or days? Do they shift with the solar cycle or react to nearby active regions? These are questions Inouye's extended observation campaigns will seek to answer. Another path forward involves cross-referencing data from other missions. NASA's Parker Solar Probe and ESA's Solar Orbiter are currently studying the Sun from within the inner heliosphere. Coordinated observations from space and ground will allow scientists to connect surface-level magnetic patterns like striations with atmospheric phenomena, such as flares, jets, or solar wind fluctuations. From a modeling perspective, these high-resolution observations feed directly into the refinement of solar simulations. Now that we've confirmed the presence of small-scale magnetic structures, future models must account for their formation, evolution, and interaction with larger systems. This breakthrough isn't just about our sun. It opens the door to studying magnetic textures on other stars too, especially those with intense activity. The same techniques could sharpen how we image distant stars or decode their light spectra. And here at home, understanding the sun's magnetic architecture with this level of detail moves us closer to forecasting solar storms more accurately, protecting satellites, flights, and power systems from the chaos of space weather. The sun may seem chaotic, but this discovery reveals a hidden order. Ultra-thin magnetic striations, once invisible, show that even the sun's surface is shaped by fine, structured forces. They raise new questions about the sun's magnetic depth and complexity. Sometimes, real breakthroughs come not from explosions, but from seeing the quiet details we've missed all along.